Here's your video for rationalizing the denominator. Our first example, 3 over radical 6. Now, rationalizing the denominator is a technique that we use before we call an answer complete or totally simplified to get rid of any radical that is in the denominator. That's considered bad form. So we have a technique we use to do some rearranging to an answer so that there won't be a radical in the denominator anymore. Now, most of the time when we're working with fractions and trying to do simplifying, we are either dividing something out of numerator and denominator or multiplying something into numerator and denominator. But the idea is we have to do the same thing to both numerator and denominator because the same number in numerator and denominator is a fraction that equals 1. And if we multiply by 1 or divide by 1, we have the same value that we started with. So we're always thinking about we have to do the same thing to top and bottom of a fraction, numerator and denominator, whatever it is that we're going to do when it comes to multiplying and dividing. So the way we can get rid of a radical in the denominator is going to be through multiplying. Seeing that radical 6, we cannot simplify that radical. We don't have any pairs of factors in this radicand. The 6, it's just a 2 and a 3. We cannot simplify this fraction, seeing a 3 over 6, because the 3 is outside of a radical, the 6 is inside of a radical. They're considered to be different kinds of numbers. We cannot simplify this fraction like we would just 3 over 6. It's not allowed. If we multiply top and bottom of this fraction by another radical 6, then what happens in the denominator? Radical 6 times radical 6 will give us just regular 6, and we don't have that radical in the denominator anymore. In the numerator, we have a 3 outside of the radical, a 6 inside of the radical. We're definitely not multiplying those to get 18. We have to keep inside numbers, outside numbers separate. So just 3 radical 6 for the numerator. Now looking at this fraction, is there any simplifying we can do? The radical still, we can't simplify that radical 6, but the numbers outside of the radicals are up for simplifying. A 3 over 6, we can think about, does that fraction simplify 3 over 6? It does to 1/2, 1 over 2. So we're able to simplify that fraction a little bit further and finish with radical 6 over 2, and that's our final answer. That's how we have rationalized the denominator in this example. The key points are, we knew that we had to rationalize the denominator because we saw that there was a radical down there. Our finished problem doesn't have a radical in the denominator, but it does have a radical in the numerator. Now we can expect that we're never able to totally wipe out a radical, only if we can somehow simplify it. But when we're rationalizing, the theme is more of taking the radical from the denominator and doing some moves to have it show up in the numerator. And I can try to give you a couple of reasons why this is a move that we learn how to do, but that's basically what we want to do and how we know that we have this problem finished. There is one thing we can do to check, however, because we're not changing the value of this expression, just changing how it looks. So if we have a calculator, evaluate 3 over radical 6, and it should equal about 1.225. If we go to the answer and evaluate this expression, it should give us the same number. And if we don't have these numbers matching, clearly we did something wrong. We should expect to see these two numbers match every single time when we rationalize the denominator. We don't want to change the value. Now, we also don't really like to have radicals approximated as decimals. Let's get those out of there. Almost all the time we prefer to work with irrational numbers in this form using the radical symbol. But maybe I can talk about why we like to have the denominator rationalized. It really started before folks had very easy access to calculators. It was important to have an idea of what these radicals equaled approximately as a decimal. Radical 6, we don't know what that is. It's not a perfect square, so it doesn't really jump out as what is the square root of 6. We can't approximate it. If we think about numbers higher than 6, we'll increase until we find another perfect square. Increasing from 6, 7, 8, 9, there we have a perfect square. We know square root of 9 is 3. If we go down from 6, 5, 4. Square root of 4 we know is 2. So that tells us that radical 6 is in between 2 and 3. There's one way we can estimate that it's about 2.5, somewhere in that neighborhood. If we do look at the decimal approximations for these, we'll see that radical 6 is about equal to 2.45, and we can even see that the radicals increase just as these numbers increase the same way. So radical 4 is the lowest, and then radical 5 is higher, and so on. They increase. Before calculators became so accessible, it was important to have these numbers memorized a little bit to a couple of decimal places. Now, if we have this expression, this fraction, 3 over radical 6, if we're interested in what approximately does that equal, we would have to do this division problem. 3 divided by, if we know radical 6 is about 2.45, we still need to try to do this division, which is tricky. Anytime dividing by a decimal, it just becomes a little bit of a tricky problem. However, if that denominator is a whole number or an integer, dividing is a bit easier. Dividing by 2, I mean, it's not so straightforward, but it's a lot easier than trying to divide by 2.45. I mean, I know 2.5 divided by 2 would be 1.25, so this is going to be even a little bit less than that, 1.225. And if you remember the decimal that we came up with when we evaluated these fractions on the calculator, it was about 1.225. So we have a better idea of the decimal value of a fraction when the denominator is not a decimal. It's a little bit easier to do the mental math. That's one reason we like to rationalize the denominator. But let's go ahead and look at a couple more examples.